All right, welcome to the morning video. So, last video, I actually, as was directed in the book, the author actually put a statement in there saying to contact him with feedback. I kind of skimmed back through that. I didn't see an official way to contact him, so I contacted him on LinkedIn. He got back to me minutes later. The correction is valid. In fact, I think in the printed copy, the correct symbol is used, but something got mixed up in the ebook. So he's going to be making that correction. All right, so moving on to the next section of the book, which is recommendation systems. Recommendation systems are techniques intended to identify or predict preferences or ratings. The association rule mining algorithms we reviewed above can be used for recommendation purposes as well. Recommendation systems are used in many fields: purchasing recommendations by Amazon, content recommendations by Netflix, etc. There are three main types of recommendation systems. Content-based. The recommendation system will profile users' interests based on the features, content of the items he/she like or have purchased. This means there is a requirement to know those features or characteristics. By identifying them, it is possible to suggest other items that such a user profile may be interested in, given the commonality of the item's features. The recommendation decision is based on the similarity of the item based on the knowledge of its content. And this is something that's exciting as well. Imagine building new recommendation systems. I think the biggest one is medical recommendations, not based on. This is where the integrity of the data gets difficult, because you go online and it's flooded with everything from you should eat raw carrot juice for the rest of your life to raw bull testicle is the key to masculinity. It's like the integrity of the data, it really matters for these. But oh man, once you get there, I mean, just imagine if you could just get recommended to you based on what you do in your life, the absolute perfect exercises, the absolute perfect diet, and instead of whenever you go online, you see an advertisement for a bacon stuffed pizza with pure lard. You constantly get reminded of things in your best interest rather than things that you can do to give money to someone else. You're constantly reminded and recommended things you can do to bring value to yourself rather than things you can do to bring value to someone else, often at your own expense for little to no return, and in fact sometimes for detriment to yourself. So the next kind of recommendation system is collaborative filtering. The recommendation system will aggregate the feedback provided by users over time about different items and aggregate those users who have provided similar feedback. Somehow is collaborative in that sense. Once that aggregation view exists, it is possible to identify other items that similar users have liked as recommended for the target user. So this is kind of, sometimes terms aren't defined the best, and it's confusing, especially for a kind of like English as a second language people. Like, there's such things as idioms, like there's expressions, there's namings that just aren't that good. And I feel like this kind of this word collaborative probably isn't that good, and the author's making a point there. It's more about aggregating, kind of grouping, clustering, rather than it is related to the word collaboration. Once that aggregation view exists, it is possible to identify other items that similar users have liked as recommended for the target user. In this case, the recommendation decision is based on the similarity of the users, based on the knowledge of what feedback they have provided historically to items. So this is the last of the three main types of recommendation systems, and it is the hybrid approach. Both collaborative and content systems have their pros and cons. Content-based requires detailed knowledge of the characteristics of the items, but that is not possible in many cases. Collaborative filtering requires building a history of user feedback so the user can be properly profiled. Sometimes the best approach is to use a combination of both. Like in any other machine learning technique, data representation is critical, meaning we need to transform everything into numbers, which an algorithm can use as input. That is particularly important as we mention the term similar. How do we measure if two movies are similar? Well, if we have a vector of characteristics and a 1 or 0 on each of the positions of that vector based on each movie's content, we can then apply the techniques we have learned earlier to compare vectors. We have seen that when it comes to vectors that represent different characteristics, features, or properties, like the number of words or words in a sentence, etc., cosine similarity works very well as a good approximation of the concept of similarity. Cosine similarity plays a key role in the recommendation systems. And remember, we learned about cosine similarity. It's a measure of distance, just like the Manhattan distance, just like the Euclidean distance. So all this stuff is going to keep coming back. Math is based on other math typically, so it should be pretty easy to go back to the other things. If we look at the introduction to the concepts part, there we go. It should be pretty easy to go back through all of the concepts. So this is the art of modeling. Is that? Oh, you know what? Maybe it's a technique. It's a technique. Oh, you know what? Actually, what it is it's a form of unsupervised learning. I guess one thing I would like to see that could be improved a bit is these these headers be a little bit more clear. When we dive into the actual so like these are fine, but once we get into the actual introduction of the concepts, the types of problems, the art of modeling, types of machine learning techniques, knowing whether or not I'll be seeing distance algorithms would help. And I guess I could know that just by knowing that we're learning about unsupervised learning and we're learning about clustering. So I guess it's probably fine as is. I don't really have the answer to how I would like it better. But let's go back and review cosine similarity. Okay, so here's cosine similarity. So now we're focusing on the angle between the vectors. And here's the graph for that. In collaborative systems, the input data is the feedback the user has provided for those movies he or she has seen. The goal, however, is to predict the feedback it would give to other movies and recommend those whose predicted feedback would be high. The input matrix is usually very sparse. There is only feedback from some users and about some movies. Okay, so here's a matrix. This is the input matrix. So we can see it's very sparse. For a lot of it, we don't have the values here because only not every user gave it a ranking. Matrix factorization of multiplicative decomposition effectively decomposes a matrix into its factors such that multiplying them will result in the same matrix. It enables the transformation of the input matrix into two new matrices with a new dimension we can call features. The intuition is what these features represent. The mathematical expression. So the intuition is that these features represent the mathematical expression of the rated item's characteristics. The two new matrices provide significant information as it is now possible to compare users by their similarity in terms of their association with the different features. Likewise, we can associate items, movies, by their similarity with their features. Somehow, the matrix factorization has automatically computed the information required by a content-based recommendation system. Various algorithms execute this process, such as singular value decomposition and stochastic gradient descent. How is this relevant to networking and clouds? Today and in the future, there are applications for recommendation systems in networking and clouds. For example, imagine a scenario where you have a network infrastructure and a team of engineers in the NOC rate in terms of effectiveness the remediation action they took for a particular problem. Connectivity lost between point A and B, and then leading to the action of rebooting the router. Such action may or may not be effective or may have different degrees of effectiveness. Such as solving the issue but causing much disruption, etc. So suppose the NOC engineer rates the action for that event. We can then see how this could enable a mechanism using the above technique to recommend actions for new problems. I can see that being very useful. So far, we have reviewed some of the fundamental algorithms in the context of unsupervised learning. Next, let's dive into the no less intriguing and exciting field of supervised learning. So that's it for unsupervised learning. It's time for supervised learning. In supervised learning, there is a target to work with. We have a label with the data. The label becomes the anchor point that allows us to train a model of some sort to accomplish the desired task. Furthermore, it also becomes the reference to determine how good or bad a model is. In unsupervised learning, for example, in clustering, it is always a bit more uncertain the accuracy of the process because there is no clear target to compare with. In supervised learning techniques, we have that reference based on the labels of the dataset we know about. course, to which extent we can extrapolate to new data that the model has not yet seen is the crucial question. It is also a big part of the complexity of the process. How well will it generalize? There are 3 types of techniques in which most, if not all, supervised learning algorithms can be grouped, depending on the type of goal. The first technique is regression techniques. And remember, this is a technique where most, if not all, supervised learning, so this is a supervised learning technique. Okay, so regression techniques. It is about predicting a number. The algorithm aims to produce a numeric value that results in the prediction for a specific variable after a given set of input variables. We will frequently refer in the machine learning context to the input variables as the features. Classification techniques for supervised learning. It is about predicting a class, a category from a well-known discrete set of options, so a limited set, a finite set. And then the last one for supervised learning is generation techniques. We want to generate new data that did not exist before. This is a field that is gaining significance, with particular techniques being used for this. As a byproduct, generation techniques can also be used for classification, as we will see later. Key takeaway: most problems in fact, can be summarized as finding a number, which is a regression technique, or finding the class, a classification technique. For the latter, it is actually about finding the probability of the classes. In practice, both are about finding a number. All right, so I'm going to bookmark that, and I want to go back and look at unsupervised learning again, because these techniques are familiar to me, and I think there were a set of techniques in unsupervised learning as well, and I want to see how those techniques changed, or if they were a part of this as well. Okay, so you know what? I think it might have been mentioned. It might have been mentioned here. Yeah, so I think it was probably mentioned somewhere there. So anyway, let's not get distracted and keep on going. So a programming paradigm shift. Before we get into the details and algorithms, I think it is good to pause a bit to reflect on what machine learning actually is. Furthermore, I mentioned this in this section about supervised learning because it may be more applicable, but could also be argued in the context of unsupervised learning. Software programming can be summarized as the art of defining a set of rules which, combined with input data, will result in a set of answers. The output of those rules, software code, when executed against the input data. So traditional programming, you feed it rules and data, and you get the answers. In the context of machine learning, there is a paradigm shift. While the ingredients are the same, the structure of a machine learning project is such that the input is the data and the answers, the labels, and the answers, the labels for this data. The goal output is to obtain the rules that govern the relationship between the input data and the answers provided. So that seems a lot more useful than you don't have to know the rules. You do have to know the answers, though. Know that the answers input could be optional. Oh, so you don't have to know the answers. And that would be unsupervised learning. In an unsupervised learning context, we do not have labels. Therefore, we do not have answers to leverage. We can still apply machine learning to the input data to obtain the rules that govern such data internally. For example, to extract the clusters inside of that data, the association rules, or the principal components. The principle of the paradigm shift still applies. Now, let's set the context to networking or cloud. In traditional networking, we would define specific operational rules like threshold cross alert TCA rules, which would be our equivalent to code. These are the human-defined rules. The data network telemetry is evaluated against the rules to get the answer, good or bad state. So here's the TCA rules, which are the threshold cross alert rules, and the data, and then we get the answer. So this is traditional networking. So in traditional networking, we have specific operational rules. So the threshold cross alert. I know what this is. So for example, broadcast storms. If you have a broadcast storm in your traffic, then the ARP traffic is going to compound upon itself in a way so that it'll flood the entire network, take the network down because there's so much traffic on it. It'll saturate every link in the network. So you can set it up so that if the ARP traffic crosses a certain threshold, then you can assume a storm is a brewing, and you can toss out all ARP traffic and then leave your network in a somewhat functional state. A few things can go wrong, but you can at the very least get in there and fix the issue. So that would be a threshold cross. Not necessarily an alert in that case, but that's a way to conceptualize what a threshold cross alert would be. If your link is saturated past 30%, you get an alert there's a lot of traffic on this link. So in traditional networking, you take your data, how utilized is your link, you take your threshold cross alert, is this link utilized more than 30%? And you get your answer. The link is oversaturated. Do something about that. As we incorporate machine learning in our network operation, there is an equivalent paradigm shift where the ingredients order is altered. So now your link is oversaturated. Here's the data for that. Here's which link it is. Here's on which device. Now using machine learning, okay, well, let's do something about that. Let's change the configuration so that there's more bandwidth on the link. Let's try to do an analysis to see what the problem is. Oh, there's a broadcast storm on the network. So your dynamic thresholds or it's misconfigured here. You had the traffic was meant to go out this way. So actually this configuration is incorrect. Here's the correct configuration. So that's a complete paradigm shift in what the role is of the network engineer. You're no longer going to be fixing things. You're going to be designing systems where AI can operate optimally. With data and labels, we can get the rules as an output using machine learning. Yeah, so the rules is instead of producing answers, you're going to work with machine learning and produce rules. Because remember what they said before, it's about automating decisions rather than actions. In our example, we get the dynamic rules that replace the static TCA thresholds. We must understand this paradigm shift. We are going to explore several techniques in the context of supervised learning, specifically in the sections ahead, where the input to the system will be the data and the answers, for example, the labels. The output of the process will be a trained model, which internally encodes the rules that connect such data with their corresponding answers. With these rules extracted, we can now infer the answers for the new incoming data, which we not have yet, and it's missing a do here. It should say, which we do not have yet. So here's the inference. So we can see this is the same as how it changed for machine learning. And I'll advance my bookmark here, delete the old one. So it's the same here. We're feeding it the answers in the data. For supervised learning, it's different for unsupervised. And we get the dynamic thresholds. So similar, the dynamic thresholds are the rules. So we feed it the labels, the answers, the data. We get the rules, and now we feed that to the inference. Now we feed it new data, and we get new answers based on that. So we can reuse this product we got from the machine learning to do more things. All right. So it is about function approximation. Any supervised learning problem is arguably a function approximation problem. We are trying to obtain the function f of x that best connects the data with the answers. All right, so we can replace the rules here with the function. It's the same thing. In order to identify that function, we have a data set, data plus labels, that we can use to train a model using a specific algorithm we choose that best aligns with the data. The fundamental outcome is the same, irrespective of whatever it is a regression, of whether it is a regression or classification problem. What the function is that aligns better with the data and the labels. If we are lucky and the problem is simple, as in the diagram below, the relationship between the input data x and the labels y is linear, and we can use a simple linear regression. More on this later. So we can see the data is linear. So here's a simple linear regression. There's kind of an extra character here. Oh, it's x and y. Very frequently, the problem will be complex, and we need a system to figure out a much more complex relationship between the input data and the expected output. In the example depicted in the picture, the input are images that may contain dogs or cats. We need a function that identifies with a 1 if there is a cat in the picture, or a 0 if there is a dog. Can you find out the type of formula or function that, based on an input image, which numerically is a matrix where each point contains RGB values corresponding to each of the pixels in the image, can produce this analysis? It is tough even to imagine. It is definitely not a linear function. It is very likely a ridiculously complex non-linear function. Okay, so to determine whether it's a cat or a dog, you need to create a function, and the function is going to be complex. Let's imagine a similar problem in our network where we have 500 different input metrics, and we want the output to be a function that provides a specific number corresponding to the type of problem that the state of such different 500 metrics and their values maps to. We could potentially find out that formula where we simply collect and inject those network metrics, and the output identifies the type of problem we have in hand. It also sounds like a pretty complex formula. So 500 network metrics all going in. Now we have, but now we have more things we can include. Interface, OSPF, BGP. So definitely that complexity is a feature, not a bug, because you need to it needs to be include a lot of different things. Both are examples to illustrate that most of the supervised techniques we will describe and see in practice can be described as nonlinear function approximation problems. The output of the process is a trained model that best approximates the function we need. With that trained model, we can feed it with new data, new cat/dog images, or new sets of our 500 network metrics, and it will produce as an output a decision, cat or dog. Alternatively, in our network example, what type of network problem it is, with hopefully a good enough degree of accuracy. More on this later. However, let's dig a bit more into a term that you may have heard before and that I have used already in the book a few times, but we have not formally described what it means. We train a model. What does this training thing mean exactly? How does one train a model? I will not go into the mathematical justification behind it, but I will describe the intuition behind the process. Okay, so how does one train a model? That's a good question, and that's a good question for another video, because the answer is going to deserve its own video. So that's it for this video. Clean up my bookmarks, and when we come back, we'll answer the question, how do we train a machine learning model? So thanks for watching, and see you in the next one.